Hello everybody, back with yet another video lesson. This one is the first one of Unit 2, which is the Systems of Equations and Linear Programming part of the class. Right, so we're jumping from the finance mathematics into a different part of mathematics. Finite math, business math is actually the combination of 3 or 4 different math classes all put together. So I apologize if this feels like a quantum leap almost from the topics that we were discussing before exam 1, but this one may be more familiar to you. We'd like to discuss systems of linear equations, not because they are the focus of what we want to talk about for exam 2, but just because we need to know about them, because when we start changing them up, when adding inequalities into the mix and start bringing in the ideas of matrices and Gauss-Jordan elimination, we want to have all of those pieces put together so that we're ready to use them in other contexts, right? But the basis of all of those tools are found in systems of linear equations. And a system of linear equations is just that. That is a bunch of linear equations put together, right, using a big squiggly bracket. Right? And what that means is that I'm not just looking for the solutions of any one equation in the system. I'm looking for the solution which solves all the equations in the system at once. Right? And of course, it's not quite so easy to see that right away. Right? We're going to have lots of methods to find, hopefully, that one solution and figure out when that one solution doesn't exist, or even worse, is not unique, where there maybe are many solutions which solve all the equations in the system. Right? Going back to our previous graphing, you may have seen graphing like this in a previous class. You might have taken a line which looks like this, y equals x plus 5, and you might have said, well, I know how to deal with that, professor. Let me grab a table of x and y values. I've been allowed to do this for a long time now. Plug in x equals 0, 0 plus 5, y equals 6. 6, right? Talk about after lunch, right? So 0, 5, I would go to my graph and I'd put the xy points 0, 5 on my graph. And I might pick another one, 1, plug in 1, 1 plus 5. This one is actually 6. Let's see. I'm going to grab my ruler, because I know ahead of time that basically this line is going to follow this 45-degree angle here. You won't necessarily know that, and that's okay. You'll probably have a piece of graph paper or be using a computer program to help you graph this stuff anyway. I might even plug in a negative number, -1. -1 plus 5 is 4. So if I followed this same pattern in this direction, I'd be at 4 on this side. And then I can connect all of those dots together to make one line. And the collection of all of these points is the graph of y equals x plus 5. This was a very useful tool in previous classes because we could talk about slopes, we could talk about y-intercepts. All of that stuff was pretty meaningful, maybe in a college algebra class or even an intermediate algebra class. We'll try not to get too much into it in this class, although knowing about slopes and sort of rise over run, it is helpful for this class. So I every once in a while, I'll mention it. Like I said, you don't have to know. You could see on my ruler here that it was a 45-degree angle that this line made. You don't have to know that. That's actually trigonometry that tells me that that angle is 45 degrees. Likewise, if I graph the other line, let's see, the other line is 3x minus y equals 1. Now, I can't plug in a bunch of, well, if I did want to plug in numbers for x and y, this one is not too bad to do that with, just because I have the y by itself. I could always plug in any numbers, but you see how for example, if I were to plug in an x value, or excuse me, if I were to plug in a y value, I could plug in from either side of this chart. I would plug that in you can probably already see that this thing is going to give me a fraction solution. Graphing doesn't work so well with fractions. We know that we can graph with fractions, but I'm really bad at graphing as it is. I'd really rather not try to graph with fractions. Right? This is a method we're not going to use that often anyway. We need to see it, we need to understand it, right? But it's not a method that we're going to use that often. So if I were to plug numbers into this equation, I would plug them in for the x's. And I'll do that because you see when I plug in the x value, the y does not need to be divided at all. Y is equal to -1. Right? That's not so bad. -1. I don't know why I marked that 4 on there. Don't need that 4. So x equals 0, y equals -1. Of course, other students might say, Professor, I know how to do this. I learned in my previous algebra class. If I can make it a y equals mx plus b thing, then I can read the slope directly out of the equation. And that's a perfectly valid way to graph lines as well. I'm going to move the y to the right side of the equation and move the 1 to the left side of the equation by subtracting 1 from both sides and adding y to both sides. Y equals 3x minus 1. This thing would, right? You might look at this and say, this is mx plus b. And in the slope-intercept form of a line, which is mx plus b, the m tells me the slope, the rise over run, and the b tells me the y-intercept. So that's a helpful piece of information to have. Right? Just because, right, if I had a graph paper, right, I guess I could have changed my graphing to graph paper today, but I didn't think to do that before class. Whoops. I didn't think to do that before class, so I won't change it now that I'm in the middle of it. I've started writing. If I had a piece of graph paper, I'd be able to count, right? Rise over run, the slope is 3 or 3 over 1. So I could go up 3 and over 1, right, and count it off and draw my line. Right? I've used a little bit of fancy math. Right? I have calculated that the angle that I'm looking for is actually 71.5 degrees. So 71 is going to be close enough. It's going to be a close match. Right? But sometimes a close match is all we have. Right? Again, if I had a piece of graph paper, I would draw this much better. Or if I were using a piece of graph paper, I would draw this much better. Right? And so my red line and my blue line, remember the line represents all of the solutions to each one of these equations. There are many of them. That's why I could use this table. By the way, the blue line, I would plug in x numbers. Those would work really easily because 3 times 1 is 3, minus y is 1, 3 minus 2 is 1. So I could find that 1, 2 right, on my graph paper, and it would be much easier to do. Again, whenever I mark something out in the middle, right, I usually mark it and label it with a whole ordered pair, x, y. And whenever things are on the axis or on the, one of the lines where you can see where it is, I don't need to give you an entire coordinate. Sometimes I will, but I don't usually need to. So all the points that are on the red line are solutions to the red equation. All the points on the blue line are solutions to the blue equation, 3x minus y equals 1. And I'm looking for a solution which is a solution to both the red line and the blue line equation at the same time. And I can see that in the graph by looking to see, is there any point that's on the red line and the blue line at the same time? That would be this point right here, the point where the two lines intersect. Right? That's the solution to both equations at the same time. Now, this would be great if I had a piece of graph paper and I could actually count where this is. Right? I would be able to see that this is 3, 8. Let me verify that I'm not lying to you. Right? Again, I solved this one before class with an actual sheet of graph paper. Right? Let's verify this solution, right? Because you shouldn't take my word for it, right? So if x equals 3 and y equals 8, let me plug that into my equations. Y equals 8 equals 3 plus 5. 8 equals 8. So that is a solution to the red equation. And 3 times 3 minus 8 equals 1. That's 9 minus 8 equals 1. That is a solution to the blue equation. So I'm not lying to you. We can verify this solution is correct. Now, again, I'm not a big fan of the graphing method, right? Because one, right, this kind of assumes that everything is nice and easy to graph. There's no guarantee that our lines will have very nice and easy to count slopes. I've chosen 2 lines here that really could be made into the y equals format with whole numbers. And these are some of the easiest lines we ever could have to graph. And even then, right, without a piece of graph paper, you still kind of had to trust me a little bit. If there were fractions all over the place here, fractional slopes, or worse, fractional y-intercepts, this would be incredibly difficult to graph. Right? And even if it were a perfect, right, line, just because they're whole numbers doesn't mean that this intersection point that I'm looking for, there's no guarantee that that intersection would fall on a perfect intersection of the grid on the graph paper. Very often what you'd have something like this where, right, the lines would intersect, you'd find the intersection point, but it's not along one of the grid lines. Right? And you'd have to ask, well, that looks like it's about halfway. Is that actually halfway? Well, maybe you'd have to zoom in. Maybe your graphing software would allow you to zoom in. Let me switch to Desmos really quickly and show you that if you're using Desmos, of course, if you're using Desmos, then it will allow you to zoom in and see other fractional solutions, not sign up, graphing calculator. And so the Desmos graphing calculator, you see how the grid lines change, right? The grid lines may not be apparent enough. Let me turn it into projector mode. As I scroll around in Desmos, you can see that the grid lines change as I zoom in and out, but there's still no guarantee, right, that this will give me something which I want. I'm just going to type in some random numbers, right? There is no guarantee that any of this will have any solution which would make sense to us. Here we go. Just random numbers, right? We can see that just by knowing what graphing is, I can tell you that, I can tell you that there is one solution here. And that's actually pretty nice that I can see that there is one solution there. That one solution, right, is at that intersection point. I could click on it and ask Desmos what it is, but it gives me these big, long, nasty decimals. Right? And the reason for that is the solution is a fraction, but that fraction is not a fraction which easily turns into a decimal. Right? Think of it like fractions over 3, 1/3, 2/3. We know those are repeating decimals, 0.33333 or 0.66666. Well, other fractions turn into decimals which repeat the same way, but maybe not in such a predictable pattern. Maybe I get that 2.889 is rounded off from 2.88888, maybe. But 3.074, I mean, that doesn't round off to enough decimals that I can see the pattern. Maybe that pattern contains 6 or 7 digits. Right? It's super not easy to see. And even if I zoomed in, do you see how as I zoom in and the grid lines change, there's no guarantee that any of those grid lines will line up with the solution. And that's mainly because Desmos graphing, right, all these grid lines it breaks it in half, maybe thirds or fourths. So there's no guarantee that the number of subdivisions that Desmos chooses to draw are going to line up. I'm trying to find one which is kind of close, but I still can't find a good one yet. Right? And you can see on the sides of my graph that I've zoomed in a really long way, and I still can't find one that kind of works. Let's see. What number is that? You can't even tell what number that is. I've zoomed in so far. The only number I see is way up here at the top, 3.0741. I can't even tell Desmos, well, how many decimal places is that? Because Desmos doesn't really keep track of it past 4 decimal places or so. It does the best it can. Right? Oh, so even worse, right? So this is kind of unsatisfying, right? If I had some magical way to figure out what exactly my grid lines should be, I could type them in here, right? Under this step. So if I magically knew, for example, the grid lines should be 1 over, so I knew the fraction part was 1 over 27 or something like that. Okay. Hey, that doesn't look too bad. Let's see. I'm going to do a little bit of fast math. That's -6 minus 21. Oh, that is exactly. I promise I did not calculate that before class. So here, 1 over 27. There's no way that you would know how to do this right now, unfortunately. And that's way beyond the scope of this class. It's not hard, but we don't need to know this. I know, because I did my quick math hack trick, that the fraction solutions will be some multiple of 1 over 27. I had advanced knowledge of that. And so I told Desmos to graph it and put all the grid lines at 1 over 27. And when I did that, the solution that you see in the graph perfectly lines up with one of those grid lines because it is a 1 over 27 fraction. And now when I clicked out of it, do you see how Desmos replaced it with this big, long, nasty decimal? 0.03704. Ugh, nasty, right? Graphing is not a solution method which I would recommend pretty much ever. The only reason we're talking about it is because it's helpful to see, right? I can see in this graph, there's one solution. And even if I didn't know the right decimals for it or the right fractions for it, I could still get a pretty good solution, a pretty good, hint of where it's at. I'm going to zoom way back out now, right, to see exactly how many over 27 that is. Ooh, nasty. I'm just trying to find the whole number. There's down here at the bottom, my finger, you can see my finger, 3. Scroll up to my line. Oh, there it is. And then over here on the left side, there's 3 as well. So there's 3, there's 3. So there's 3 and there's 3. So I need to go 1, 2, 3 over 27 back from 3. So that's 2 and 24 over 27. Blah. And then 2 up from 3. So that's 3 and 2 over 27. Nasty, nasty, nasty. Right? And again, all of that, I couldn't even do that if I didn't magically know that 27 was the right fraction. No way that you can tell in this class. Right? So my point with this nasty decimal is that graphing is a good method to understand, right? But it's not a method that we're going to use that often, right? I put a few questions about it on the homework just because I wanted you to be able to see the graphs. We're going to be making lots of graphs in this unit, And we have to know how to find these solutions, but we won't actually go to the graph to find the solutions out of the graph. More often, we will actually draw the graph and then use one of the other methods to find the solution. Right? So it's a good review if nothing else, right? So please don't get scared off by the fact that I just threw a bazillion decimals at you and it looks really nasty, right? And the solutions for the ones that are in the homework should be as easy as the ones that I started with in OneNote, right? They should be whole numbers and they should intersect at nice, clean graph paper grid lines, right? So if you had a piece of graph paper, do them like that, right? Or if you wanted to use Desmos, it should be able to show on the grid lines without you having to type in a magical fraction step like I did, right? All the graphing ones should work that way. So to solve by graphing, right? Let's plot both lines. That's the list of steps, right? The y equals mx plus b form will help here. Or at least the ones, if it can't work with y equals mx plus b that easily, I usually wouldn't ask you to do it by graphing. And once both lines are found, right, find the intersection. And that intersection is the solution. Notice how the solution is both at the same time. This intersection is actually x equals 3, y equals 8. And both of those together are one solution to this system of equations. Right? It's kind of weird because we're not used to one solution being represented with multiple numbers. Right? But here, remember, I'm trying to solve the entire system. I need to know the value of all the variables in the system, which make all of them true at the same time. Right? So if our solutions, if I had x, y, and z, right, I wouldn't be able to graph that, of course, because that's a three-dimensional thing. Right? The solution would be x, y, and z. I need all three of them to tell me what the solution is. Later on in this unit, we're going to have 7 or 8 variables, right? We definitely won't be able to graph that, right? But I'll need all 7 or all 8 variables to tell me one solution to that system of equations, right? So luckily for us, right, the graphing method problems are usually the easier ones that we don't have to, that we don't have to worry quite so much about. Pull up the keyboard again. When I pull up the keyboard like that, you saw me just do my on-screen keyboard. When I tap and the little cursor comes up, the keyboard doesn't pop onto the screen, you know, like it happened, like it just did a minute ago. And so that's a nice trick that I figured out. Right? Hooray, Professor Trevino, for figuring out something probably a lot of other people knew a long time ago. So solving by graphing is usually as easy as plotting both lines and finding the intersections. Because we are only using lines and systems which line up, right? I'd say this is the easiest solution method, but only because the easiest problems are done with graphing. Right? The harder problems we can't even do by graphing because that's where all the nasty fractions come in. But on the graph, we can see that graphing problems and systems of equations problems, right? They could have one solution. SOLN is the abbreviation for solution. Right? You can imagine graphing two lines together. It's possible that the two lines never intersect at all. They're perfectly parallel. That would mean there's no solution. And if I were to graph these two lines and then they lined up exactly on top of each other, it's kind of hard to draw a line directly on top of another line. So I'm going to draw it squiggly like that. Right? That's both lines directly on top of one another. Those two lines would share every single point. Right? That would be infinitely many solutions. We'll discuss more about the infinitely many case later on, because later on in this unit, whenever we bring in inequalities, greater thans or less thans, everything we do is going to be an infinitely many solutions case. But for now, I would focus more on the one solution, no solutions when you're doing graphing, because we see a lot more of those and we see the rest. So graphing is one of those methods that you practice it a few times, it kind of works, you kind of understand it, and you kind of put it up on the shelf. It helps to see it, it helps to understand it, but it's not a method that I will ask you to do too many times. I'll try not to even ask you to do one of those on the test, although depending on how many other questions there need to be, there might be one on the test that asks you to do it that way. Solving by substitution happens a bit more, right? It's a bit more common because solving by substitution is an algebraic method. It doesn't require a picture at all. I can do this just working with the x's and the y's. I'm going to do the same system of equations which we had before. So if you remember, the solution I know in advance is already 3, x equals 3, y equals 8. Right? So step 0, right, it's not really a step, it's just something we need to know going into this, is that we assume there is a solution. And more specifically, assume there's one solution. If that solution is broken, because we know it can be, there can be 0 or it can be infinitely many, we're going to have to learn how that messes things up. Right? Because we're going to recognize that it's messed up, say, oh, it must be broken like that because there's no solution. So we'll assume that there is one solution, right? That allows us to say, well, the two x's are the same x values, and the two y's are the same y values. Right? Basically, x's and y's are equal. Right? And what I mean by that is the x and y don't have to be the same number, but the x in equation number 1 and the x in equation number 2 are the same number. And y in equation number 1 and y in equation number 2 are the same number. Right? And I know it seems kind of weird that I have to specify that. Right? Most people wouldn't even bother calling that to your attention, which is why I called it step 0. But that is an assumption that we are making. We are assuming that there is one solution before we get into this. The real step 1 that most people will begin with is to isolate one variable. And that can be either variable, and it can come from either equation. It does not matter which. As long as the variable is by itself, it can work here, because what we're going to do is we're going to plug it in for the other one. Right? This particular system of equations already has y by itself in the first equation. So really, I don't have to do any work whatsoever. This part is already done for me. Y equals x plus 5. Right? You may have to, for example, if I were to do this in the second equation, let's say I completely blacked out and I forgot, and I looked at this system of equations and I said, Professor, I'd like to get this y by itself. I like that because it doesn't have a number in front of it. Right? I don't need to divide by anything. Well, I might add y to both sides or subtract 1 from both sides. Right? I'll move it around with algebra. Right? I like picking things which don't require division. No division means no possibility of fractions. Makes me much happier. But y equals x plus 5 was kind of already given to us already. Once we have that, we will substitute this into the other equation. You can't plug it where you started, because if you plugged it back into the same place where you started, that's circular logic, right? You'd end up with like 5 equals 5 or something like that. It wouldn't work out. You wouldn't actually be able to find a number at all. So I'm going to start with the other equation, 3x minus y equals 1. And then I'm going to plug in y equals x plus 5. And I'll even use my red pen, right, to emphasize the fact that y equals x plus 5 came from step 1 equals 1. Now this particular problem, I will have to distribute that negative sign that you see in front of the red parentheses. I need to add some more space. 3x minus x minus 5 equals 1. And I know that that might not feel super great, but now this has one variable in it. I've been solving equations with one variable in it for a long time now, right? So this just becomes quote unquote regular algebra. 3x minus x is 2x minus 5 equals 1. Add 5 to both sides equals 6. And then divide by 2. X equals 3. So this is part of the solution. Remember, the solution required both an x variable and a y variable. I had to know both of them to count that as the solution. This tells me that if there is a solution, then x has to be equal to 3. Remember, that's that step 0. Right? So assuming there is a solution, the x has to be 3. Let's see if we can actually put together the other half of the solution. More space, please. Step 3. Once you've found that part of the solution, you can plug that anywhere. You can think about that as once we found x equals 3, that is a mathematical period. My chain of logic has now ended. Right? If there is a solution, step, then x equals 3, period. Now that I know x equals 3, I can take that back up to the top and plug it in anywhere I want to. Right? It will be easiest to plug it back into step 1 because you see how y has already got x away from it, right? I could plug in the number 3 there very easily. But if for some reason you don't like that, or you see another place farther up in the original problem where it would be easier to plug it in, go for it. Anywhere is fine. Y equals x plus 5. And I'm going to plug in the 3 that I already figured out from step 2. Tells me y equals 8. Now, a mathematical period, now I have both parts of the solution. X equals 3, y equals 8. That's the full solution. If we were doing this on a graph, that's where the intersection would be. If you were typing this into my OpenMath, you might need to type it in as 3, 8. That's okay. It means the same thing. Right? But I could plug in both of these numbers back into the original problem to check my answer. I like checking my answer sometimes. Right? Let's see. So 3 plus 5 equals 8. That's good. 3 times 3 is 9, minus 8 is equal to 1. So you can just mentally plug it in really quickly like that. And anytime the numbers don't work when you plug them back in, you've made a mistake somewhere. It's called solve by substitution. And it really only, I won't say only, you can do solve by substitution even when there are fractions present. It's just less common to do so. So I'll say this about solve by substitution. Solve by substitution works best whenever one variable does not have a number in front of it. Like 2x or 3x, right, or 5y or 19x. It works best when one of the variables does not have a number, that is, that hidden invisible one is there. You have 1x or 1y in one equation. And again, that hidden one might not be visible. It'll still work, right? In all the other cases, but the other cases will involve fractions, and we're going to try to avoid those fractions. Matter of fact, the last solution method that we have, the addition or elimination method, will be a way that we can do basically the same process, but it'll allow us to not have fractions whenever one of the variables is not 1x or 1y. So that's pretty neat. Let's go down. I'll take out that extra space after the video is finished. Okay, so let's solve by substitution. Oh, sorry. Yeah. I was just going to list the steps before we move on. So step 0 is assume there is a solution. Assuming that there is one solution, isolate one variable from one equation. It doesn't matter which one. It doesn't matter where it came from. EQN, by the way, is the abbreviation for equation. Isolate one variable from one equation. We'll plug that in to the other equation and solve. Because when we plug it in, two variables becomes one variable. One variable is something I'll be able to solve. Right? You'll be able to have a partial solution at the end of step 2. Once you have that partial solution, we'll plug in that partial solution to find the full solution. And you can always check your answers by going back and plugging them into the original equation and the original system. It should make all of the equations true at the same time. And that's solved by substitution. And again, right, no one says this has to be perfect the very first time you do it. I know the homework, there may only be 3 or 4 homework questions about each one of these methods, but you can search for systems of equations, practice solved by substitution. You can pull up lots of different examples. If you'd like me to make up a few, right, just email me. Right? There's plenty of stuff out there. So that's solved by graphing. We said that was an okay method, but it was a special case method, really. We have solved by substitution, which is an okay method too. It's algebraic, so I don't have to have a picture anymore. But it feels like a special case. Like it feels like I can only do that whenever there's a 1x or a 1y. We know that's not true, but it just becomes much harder when it's not that way. So there's got to be another way, right, that's a little bit more general than this, that we can rely on even when we don't have one of those quote-unquote easy forms of the line. Right? And that's the solve by elimination method. Notice how in this example that I've written down, none of the variables are 1x or 1y. That is, if I tried to solve this system with substitution, it wouldn't work so well, right? I mean, it would be really nasty. I could subtract 2y from both sides of the first equation and then divide by 3. You see how nasty that fraction is? And that fraction would have to be plugged in to the second equation. I don't want to do that. Like I said, if you can keep track of that, go for it. It will work that way. But I don't like that. That doesn't seem like something I would want to do. And so let's talk about another method called solve by elimination. Step 0, we're going to make that same assumption. There is one solution. Remember, that assumption allowed us to treat the x's and the y's as the same x's and the same y's, and I could start putting them together. And without that assumption, everything falls apart. So now that I have this assumption, I've made this assumption, now all the x's and all the y's are the same x's and the same y's. And so we're going to use a little trick, right, called adding everything on the left side and adding everything on the right side. Because if you think about it, whenever I tell you an equation like this, let's say, for example, 6x plus 5y, that's the same thing as 2. So I'm used to doing something like this. I'm used to adding 5 on both sides of an equation. It feels totally natural to me. I've solved equations like that forever. Or maybe I have solved equations by multiplying by the same number on both sides. I'm totally used to doing something like that. But with the elimination method, all it's doing is it says, well, if 6x plus 5y equals 10, then why don't we add 6x plus 5y, equals 2. Why don't we add 6x plus 5y to the left side, that is, add all these things on the left, and add 2 on the right side, because 6x plus 5y is 2. And so I am adding the same thing on both sides of the equation, it just doesn't look the same. But I know they're the same because I know 6x plus 5y equals 2. I'm not sure that's super helpful here because I can combine my like terms. But do you see how this still doesn't helpful? I mean, this is not very helpful because nothing cancels, right? If they did line up, then this would be really helpful to me, right? If I had 3x on one and negative 3x on the other, this would make my life way easier because they would cancel out. But because nothing cancels out right now, I don't think that's super helpful. I'm going to rewrite the problem one last time because I'm going to show you how we get around this problem. Whenever we have a problem like this one, do you see how I have a 3x and a 6x? Well, I could make them to where one of them was a 6x and the other one was a negative 6x. And you might, if you've ever seen this method before in a previous math class, you might be saying, well, yeah, that looks really easy, Professor. Let me show you how that works. I take everything on the top equation, multiply it times 2. 2 times 3 is 6. But let me multiply it times negative 2, so that negative 2 times 3 is negative 6x. That would match up with the positive 6x below it and cancel each other out whenever I add them together. Okay? Of course, I can't do that for free. I have to do the same thing on the right side of the equation. And I know what you're thinking, Professor, what if the y's matched up, right? You could do it with the y's just as well, right? As long as one of them matches up, this method will work perfectly. And you can always find some kind of multiple to make it match up. I know in this one, I kind of had to do a little, it almost feels like common denominators, right? I had to think about, well, what's the common multiple of 3 and 6? Well, it's 6. How do I make it 6? Well, I need to do 3 times 2. And 6 times 1, I didn't actually show the times 1 here because I didn't need to, but that felt very much like common denominators in fractions. If you wanted to do this with the 5 and the 2 on the y's, well, let's see, the common multiple there is 10. I could multiply the top one by 5 and the bottom one by 2 to make them both of the y's equal to 10y. I would just have to make sure that one of them was positive and the other one is negative, right, to make that happen. Okay, so we'll come back and we'll do that afterwards. But for now, let me work with just the x's. Okay. I targeted 6 because I saw that 3 and 6, the common multiple is 6. And to make 6, I needed 2 times 3. And I had to make sure one was positive and one was negative. So I multiplied the first equation times -2 and the second equation times +1. That would give me -6x minus 4y equals +6. +6x plus 5y equals 2. Right? I only cared about the x's because once x's cancel out, I'll pick up the pieces, right? I'll solve from there. The only thing I care about right now is making these x's cancel out. And when I add them together, they do. -4y plus 5y is 1y equals 8. And wouldn't you know it, that's the partial solution we got in step 2 of the substitution method. Hey, we didn't have to do a whole lot of nasty anything for that. Right? As a matter of fact, as long as we had this idea, this almost common denominators like idea, understood and practiced that a few times, I bet you that would actually be really easy. Because when you're multiplying, you can always multiply by the other number, right? That is, if I looked at that 3 and the 6, I could have made that common multiple 18 because 6 times 3 is equal to 18. Multiply the top one by 6, multiply the bottom one by 3. I mean, yeah, the numbers will be a little bit bigger, but so what, right? We've got calculators for that kind of thing. We don't need to guarantee that we always find the lowest common multiple, right? As long as you get the right answer, do it any way that feels good to you. Once I find that partial solution, I'm going to do just the same as before. 3x plus 2. I'm going to plug in that partial solution 8 equals -3. 2 times 8 is 16. I will subtract 16 from both sides of my equation. -3 minus 16 equal to -19. Divide both sides by 3. Oh, goodness. Okay, so this is what I was afraid of. We're going to have fraction solutions. Remember how we said that graphing doesn't work so well when you got fraction solutions? This worked out okay with a fraction solution. X equals -19 over 3, comma, y equals 8. That is the full solution. You could put that in an ordered pair, like so. That's how it would look. Not too bad. I mean, it looks silly, I know. You could even go back up to the top and plug these numbers in. Right? 3 times, what was it, 19 over 3? -19 over 3. The fractions would cancel to leave -19 plus 2 times 8. Yeah. 2 times 8 is 16. So -19 plus 16 is -3, right? You could plug it into the second equation as well to make sure that those numbers actually work out, right? And I seriously hope they do. Someone will correct me by email if I've made a mistake. But having fraction solutions to systems of equations is not uncommon. As a matter of fact, having whole number solutions is super uncommon, and we have to go way out of our way to make up problems to make sure that they're whole number solutions. I can guarantee you that most of the problems that will work in this class will have fraction solutions. And yeah, they look silly. Yeah, no one likes working with them. But fractions are just a part of life. Decimals are just a part of life. Right? We can't always get away from them. By the way, I'm going to write the original problem down again. 3x plus 2y equals -3, and 6x plus 5y equals 2. Because if I wanted to solve this, and I wanted to work with the second equation and the y's, I could. You see, to make the y's go together, right, I need to multiply the top equation and the bottom equation by something so that the y's match up. And if I have 2 and I have 5, well, why don't I do 10? I'll multiply the top equation times 5 and the bottom equation times 2. That makes 10 and 10. But in order to make them cancel out, one of them has to be positive 10, other has to be negative 10. You can choose either one of these numbers to be negative, by the way. Right? Just to show you, I'll choose the second one to be -2. In the first problem, I chose the top one to be negative. But as long as one of them is positive, the other one's negative, it does not matter. 15x plus 10y equals -15, multiplying everything in the top equation times 5. Multiply everything in the bottom equation times -2. That gives me -12x minus 10y equals -4. And when I add these things together, this is how I do it, by the way. I put the plus sign outside the little bracket notation. It just helps whenever you're doing your work by hand. Right? And when you show this, remember on the test, you're going to have to do this method. And so being able to notate your work is important. So I like to practice showing good work. When they add up, they cancel out, at least the y's do, and leave behind 3x equals -19. Or x equals -19 divided by 3. That's the partial solution. And I know what you're thinking, Professor, you told me I have to plug in that partial solution somewhere else in the equation, right? Right? Yeah, it sucks to plug in a fraction. Sometimes, whenever I see students get a fraction for their partial solution, rather than go back and plug it in as a fraction, because it's not always going to work out so nicely, what they do is they say, you know what? I know that my x equals -19/3. Let me go back to the beginning and start a different elimination. Do you see how I could have done this other elimination right afterwards? And so I could get a partial solution for y, put that together with a partial solution for x. It doesn't require any plugging in whatsoever. It just requires 2 different elimination steps. Right? So you always get that choice. Right? You could plug in to find the full solution from the partial solution, or you could go right back up to the top and eliminate a completely different way. Right? Just make sure you eliminate x's one time and y's the other time. That way, you'll actually get both parts of the solution. You get that choice. Okay? And then you could go back and plug in these numbers to verify the full solution is, where was it? There is -19/3, 8. So that's the nice part about this solve by elimination method. As a matter of fact, whenever we do matrices later on in the week, whenever I do my second video for the week, it will be all about matrices. Elimination and addition method, this last method, is the basis, is the foundation of all the matrix stuff. So I would practice this method. I think on the homework, there's only 2 or 3 problems about this method specifically. but I would seek out additional problems. I would find more and practice more this elimination method. It's not going to exactly be the same thing as what we talk about with matrices on Wednesday or later in the week, but it is a very good foundation for everything in this unit after now. So this elimination method is really nice. Let's put this solve by elimination steps down at the bottom here. And I'll make that black. Solve by elimination. Step 0, we make that assumption. That assumption is what lets us treat the x's and the y's as the same x's and the same y's. And like I said, most textbooks, most teachers, they won't even bother telling you that. Shame on them. But we make that assumption silently. Step 1, if necessary, multiply the equations so that one term would cancel out. What I mean by that is they're the same number, one positive, one negative. Right? So plus 5 minus 5, x, plus 8 minus 8, y. And you can always multiply by a number big enough, right, to make that happen. And you saw when I kind of just multiplied by each other's numbers. That's a good way. Sometimes it's going to end up with a big number, but that's okay. I can deal with big numbers. Right? Calculators help me deal with big numbers all the time. Right? Well, if I have a method, then I just have to follow the numbers. Right? I would much rather work with fractions or decimals and big numbers than not know what I'm doing at all. And that's the great part about math, is that once you figure out the method, right, everything just kind of falls into place. I multiply by some numbers. Sometimes you won't have to do this, by the way. Sometimes you will already be ready to eliminate. So you won't have to do step 1. Step 2, add the equations together. One will cancel. One variable will cancel. If you did your step 1 correctly, one variable will cancel out whenever you do step 2. Add those equations together. You solve. That will give you your partial solution. Right, your x equals blank or your y equals blank. In step 4, you get to choose. Either you can plug in the partial solution, in step 3, right, to figure out what the other half of the solution is, or you could do a second elimination to figure out what the other half of the solution is. A second elimination would essentially send you back to step 1. Right? Only when you multiply, you've got a different target in mind. Right? Either one of those is okay. Right? Most of the time, you're just going to be plugging in because it's easy enough to plug it in. Every now and again, especially when you get a fraction for your partial solution, it will be easier to go back and do a second elimination. But whichever method works best for you, works best, right? Try it both ways. See which one you like. And I know it feels like we had a bunch of steps. We had 3 or 4 different methods, 3 or 4 different steps in each method, right? I don't have these things memorized. I know it feels like I know everything sometimes, Professor, you just have all this stuff perfectly memorized. But it's not necessarily true, right? You've seen me make lots of mistakes before, and that's because I know the basic idea of what I'm doing. And I just make up this list of steps, and it looks a little bit different every time I do it. Right? This time it had 4 steps. Right? But maybe next semester when I explain this same process, it'll have 3 steps, because maybe steps 2 and steps 3 I'll smush together as add the solutions together, or add the equations together and solve for the partial solution. Right? There's nowhere there's a big book, right, that says this is math. You must follow these steps. I guess math isn't a list of steps. Right? For the same reason, right, memorizing a bunch of recipes doesn't necessarily make you a good cook. Right? Memorizing a bunch of steps doesn't necessarily make you a good mathematician. Right? If you cook, and if you're good at cooking, you know that there's a lot of art to it. It's about what feels right, what tastes right, what looks right, what smells right. Math is the same way. I'll look at something and I'll choose to do something different just because it doesn't look right. Right? Or I'll choose, you know what, that fraction gives me the heebie-jeebies, right? I'll go a different way just because it doesn't smell right when there's a fraction there. Or I might look at something and say, well, I didn't expect a negative number there, right? Maybe I made an error somewhere earlier in my process. There's a lot of that in mathematics, right? And I know that people don't always see that, or they don't always appreciate how much of the art there is in mathematics, just because whenever you're learning, quote unquote, like algebra, college algebra, basic algebra, right, or business math, right, it feels like this has been done and humans have been able to do this for thousands of years. That may or may not be true, right? Humans have probably been able to solve systems of equations like this for a long time, but not as long as you think, right? So we're actually not that far off from craziness, right, that you might study in a calculus class if you took calculus. I know that this class doesn't usually end up with students in calculus, but maybe you're going to be in my 1325 class, my business calculus class next semester, right? And even a business calculus class, right, the calculus ideas come from the 1800s, right? If you want to get, 1600s is when they were first found, but the 1800s is when we actually proved that the stuff actually worked. They were just interesting patterns in the 1600s, right? So it wasn't that long ago. And I know it feels like 400 years ago. It's got to be a long time ago. But humans have been around on this planet for a lot longer than that. So 400 years out of thousands and thousands and thousands and thousands of years, right? It's actually a pretty recent thing. So don't feel like everybody on the planet has always understood this and you're the nasty one out for not getting this right away. There's a practice to this, right? So practice this stuff. It's going to take time, it's going to take effort. And if you can do this, it's actually a really great thing, right? This is not something that is supernatural for everybody. And I know that, right? I had to practice this stuff when I was learning it too. Anyway, I'll be back later on in the week with a video about matrices and the matrix solution methods that may be a little bit less familiar to you than the graphing, elimination, and substitution methods that are in the first part of the week. Right? Everyone have a good week. I'll see you later on.